In this lesson, we're going to go over Rolle's theorem. Rolle's theorem, and its more general version, the mean value theorem, are very important theorems in mathematics because, as we'll see, the mean value theorem is used in the proof of the fundamental theorem of calculus. And this is one of our most important theorems in all of mathematics. So that alone justifies our study of the mean value theorem and Rolle's theorem. So let's take a look at Rolle's theorem. It makes this statement. So Rolle's theorem states that if a function f of x is continuous on an interval ab and differentiable on the interval ab, on the open interval ab, notice how this interval is open, and f of a equals f of b, then there is a number c in the open interval ab somewhere in which the derivative of f evaluated at c is equal to 0. So that's Rolle's theorem. Notice we have three conditions. F of x must be continuous on the closed interval. It must be differentiable on the open interval ab, and f of a must equal f of b. If you have these three conditions holding, then you can conclude that there is a number somewhere in between a and b in which the derivative of f is equal to 0. Now let's take a look graphically at what this is telling us. So down here we have the graph of a function. Here we have the graph of some function. Notice that, let me move that back a little bit there, okay. Notice that this function, let's say that that's our point A is 1 and B is 5, and this function is continuous from 1 to 5. Doesn't have any breaks in it. It's also differentiable. Notice that there are no sharp cusps in this graph. It's not broken anywhere. It's nice and smooth. So it is going to be differentiable as well. So, and also notice that f of 1 is 0 and f of 5 is 0 as well. So f of a equals f of b. So graphically it looks like this satisfies all the conditions for Rolle's theorem. It's continuous, it's differentiable, and f of 1 equals f of 5. Now, if we take a look at tangent lines along this graph, so here we have a tangent line moving along the graph. Notice that at some point we're going to have a maximum value for this function the way it's drawn. At that maximum value, notice that our tangent line is horizontal. So right here at this point, which in this case it looks like 3, that's going to be our c value. Notice that at that point f prime of c is equal to 0 because our tangent line is horizontal and the slope of a horizontal line is 0. So this illustrates why Rolle's theorem is true. Now the proof of Rolle's theorem we're not going to look at right now. We're just going to look at some examples. We'll do that in a separate video. Let's look at a few examples. So we're going to have a sequence of examples here, and we want to determine if Rolle's theorem can be applied to the following functions, and if so, we want to find the c value in which f prime of c is equal to 0. So let's look at this function first. We have f of x equals x squared minus 3x plus 2 for x between 0 and 3. So this is over the interval from 0 to 3, closed brackets. So we need to check three things. Is f of x continuous? Is it continuous over the interval from 0 to 3? Well, it's a polynomial, and we've seen before that yes, polynomials are continuous everywhere over all the real numbers. So yes, that is certainly true. Is it differentiable? Does the derivative exist on the open interval from 0 to 3? Well, in this case, the derivative is 2x minus 3, and certainly this exists for every x in the interval from 0 to 3. It exists everywhere, in fact, for all real numbers. So yes, the function is differentiable on the open interval. And then 3, we just need to check, does f of 0 equal f of 3? Well, let's see, f of 0, if we put 0 in here for x, we get back 2, of course. And if we look at f of 3, we're going to get 9 minus 9 plus 2, and that's equal to 2. And yes, these are equal. And so this holds. So yes, all three conditions for Rolle's theorem holds. So now we are guaranteed that the c will exist. This number c will exist where the derivative is equal to 0. So now all we have to do is set the derivative equal to 0. And solve for x, and that'll give us our c value. So the derivative is 2x minus 3 equals 0. Solve that for x, take the 3 over, divide by 2. We're going to get x equals 3/2. And that's our c value. And graphically, if we look at the graph up here, we see right here here's f of 0. Here's f of 3 right here. This might be a little small for you to see. That's 3 right there on the x-axis. That's 0 right here. We notice f of 0 equals f of 3. They're both equal to 2. And the c value that we found is 3/2. That's right here. That's our c value. And notice that the derivative at that point is 0 because our tangent line is horizontal. The slope of that line is 0. And there we go. So we could apply Rolle's theorem to this function. Now let's look at this example. Now let's see if we can apply Rolle's theorem to this function. F of x equals 3 minus the absolute value of x minus 3 over the interval from 0 to 6. Now down here we have the graph of this function, and you can obtain this graph if you start with the graph of the absolute value of x. That just looks like this. And then replace the x with an x minus 3. That will shift this pointed vertex 3 units to the right to 3 when you do that, and you'll get this. And then put a negative in front. When you put a negative in front of the absolute value, that will shift this graph upside down. It'll shift it upside down. It'll flip it about the x-axis. And then when you add 3 to it up here, that will move it up. And then you'll get this graph right here. So this is the graph of, right, and that's obtained from going through a step-by-step process starting with the absolute value of x. Now, at each step along the way, starting with the absolute value of x, this is a continuous function, and each step along the way, you don't put any breaks or vertical asymptotes into the function. So at each step along the way, your function is going to be continuous. So this function is continuous. So the first part of Rolle's theorem is satisfied. This function f of x is continuous on the interval from 0 to 6. That's no problem. The third part, let's look at that first, or second. F of 0, if I put 0 in here for x, I get 0 back. And f of 6, if we put 6 in here for x, we get 3 minus 3. That's also 0. So f of a equals f of b. That holds. But the second requirement that f of x be differentiable, well, if we look at the graph here, we see that f prime of 3, there's a point right there on the graph, a cusp. So f prime of 3 does not exist. So therefore we cannot apply Rolle's theorem. Alright, so we cannot apply Rolle's theorem in this case. And in fact, the conclusion of Rolle's theorem does not hold. We can see that at every point from 0 to 6, the derivative of our function is never 0 anywhere, right? All along here, the derivative is 1 because the slope of our tangent line is 1 everywhere from 0 to 3. Then from 3 to 6, the slope of all of our tangent lines are negative 1, so our derivative is negative 1 from 3 to 6. And at 3, our derivative does not exist. So at no point from 0 to 6 does our derivative ever equal 0. So f prime of x is never 0 from 0 to 6. And so we see that the conclusion of Rolle's theorem doesn't even hold. And that's because the derivative does not exist at one point between 0 and 6. All right, now let's look at this example. Now here we have the function f of x equals x squared minus 1 divided by x, and we want to consider it over the interval from negative 1 to 1. So first thing we have to check out is it continuous over negative 1 to 1? So, well, we can see right away the answer is going to be no, because if we look at the denominator here, that's equal to 0 when x is equal to 0, and we see that 0 is in this interval. So f of x is not continuous over, because f of 0 does not exist. Notice also if we try to actually evaluate f of 0, we get negative 1 divided by 0. Well, that's the form of a vertical asymptote. And if we look at our the graph of our function over here, we see that at x equaling 0, this function does have a vertical asymptote at x equaling 0. So we cannot apply Rolle's theorem in this case because our function is not even continuous over the interval. Also notice that if we look at any point on the graph between negative 1 and 1, it doesn't look like there's any place where our tangent line would be horizontal anyway. So there is no point where the derivative would equal 0 between negative 1 and 1. Alright, so let's take a look at this example now. What about this one? So f of x equals sine x over the interval from 0 to pi. Well, let's check it out. First of all, is the function continuous? Well, yes, because the sine function is continuous over all real numbers. That's one of our properties of the sine and cosine function that we considered in the section when we were studying continuity. So yes, that does hold. The function is continuous. Is it differentiable? over the interval from 0 to pi with open parentheses? Well, yes, because f prime of x equals the cosine of x, and this exists over 0 to pi. It's defined everywhere, in fact. So, yes, it is differentiable. Third thing we need to check is, does f of a equal f of b? Well, let's see. F of 0, that's going to be the sine of 0. That is 0. F of pi, that is the sine of pi. That is 0. And yes, they are equal to each other. So that checks out. So yes, this is true. So we can apply Rolle's theorem. Now let's find the number c. So what we have to do is we have to set f prime of x equal to 0 and solve for x. So our derivative is cosine of x. And where does that equal 0? Well, that's one of our basic trig functions, and that is going to equal 0 between 0 and pi at x equaling pi over 2 for x between pi and 0. And so that's our c value. And you can see that graphically by looking at the graph of the sine function. Here's its graph from 0 out to pi. Notice that we have the peak right there. That's where our derivative is equal to 0, because that's where our tangent line is horizontal, so it has a slope of 0. And that point right there, of course, is halfway between 0 and pi. That's pi over 2. So that's the c value where the derivative of our function is equal to 0. Now let's look at this example. So we want to look at f of x equals x squared minus 3x plus 2 for x between 0 and 5 halves. So over the interval from 0 to 5 halves. So first of all, is this function continuous on the interval from 0 to 5 halves? Well, certainly it is, because it's a polynomial. Polynomials are continuous everywhere. Is it differentiable on 0 to 5 halves? Like that? Well, certainly, because the derivative is a polynomial, and its derivative is 2x minus 3, which exists on this interval. So yes. Third thing we need to check, does f of a equal f of b? Well, let's see. So f of 0, that's equal to 2. And f of 5 halves, or 2.5, well, that's going to be 5 halves squared minus 3 times 5 halves plus 2. And you can evaluate that on your calculator or do it by hand. You're going to get back 3/4 or 0.75. Well, okay, now we see there's a little problem because this does not equal 2. So no, this does not hold, so we cannot apply Rolle's theorem in this case over this interval. And we can see from the graph of the function right here that that is certainly not true. Right here's the graph of our function. There's f of 0. Here is f of 2.5, and we see that their heights measured along the y-axis are certainly not equal. This number does not equal this number, so f of a does not equal f of b, and we cannot apply Rolle's theorem. All right, so that concludes our discussion of Rolle's theorem.